It's my great honor to introduce Rachel, who's going to be doing the first talk of the evening. Rachel just recently finished her degree in digital audio engineering at the University of West London and started working as a C++ software engineer. And today she's going to continue her series on DSP introduction talks. And that's number 2 in the series, right?
Yeah,
so
last month we did.
That's very exciting. So please give a warm welcome to Rachel.
Thank you. Thanks, Timar. Hey, everyone. This is my first in-person talk for the audio program Meets. And this is, like Timar said, the second episode. You'll have to excuse me. I'm not so used to public speaking, and I'm recovering from an illness. So if I need to take a drink or clear my throat at any time, please bear with me. So today we're going to be talking about common signals and transformations. The objective of this is just to look at some common signals, their notation, familiarize ourselves with some common operations on signals as well. And yeah, just get some understanding of some fundamental DSP concepts. So the first thing I'll mention is that all the signals and operations we'll be looking at today are discrete time or digital. I may occasionally make reference to continuous time counterparts, but I'll do my best to make the distinction if that happens. If you're familiar with DSP notation, or you tuned into last month's DSP Corner, you'll recognize that I'm using square brackets and the independent variable n throughout the presentation, denoting discrete time signals and systems. The first and potentially the most significant signal I'm going to speak about today is the unit impulse signal. This is sometimes referred to as the impulse signal or the Dirac delta, though the latter is usually reserved for the continuous time counterpart. The words signal and function are generally used interchangeably, so you can assume I mean the same thing whenever those terms are used. How is it that such a seemingly simplistic signal, such as the unit impulse, could be so significant? Understanding the power of the unit impulse and how any digital signal can be expressed as a sum of weighted, shifted impulses is the key to understanding essential DSP concepts such as linear time invariance and convolution. First, let's define the unit impulse signal. We introduced this notation briefly in last month's episode. On the left of the equality is the notation for unit impulse signal. We use the Greek letter delta here to express that this is a unit impulse signal. On the right-hand side of the equality, the signal is defined for every integer n. We can see that the unit impulse signal is a signal that has a value of 0 everywhere, aside from n equals 0, where it has a value of 1. Impulse decomposition is the first step in understanding the fundamental DSP concept of superposition, which we will work up to and gain a basic understanding of today. Say we have an arbitrary signal x of n in the top corner here. We can decompose it into a sum of weighted shifted impulses. But before we do that, it's worth mentioning that x of n is an odd signal. And by that, I do not mean that it is peculiar. I mean that it has odd symmetry about the y-axis. This axis highlighted in red here. The conditions for oddness are as follows. X of minus n equal to minus x of n. This way we can check the above signal for oddness. I'll come round in front. So what we have to do when we check conditions like this is just plug in a number for n. So let's say we plug in 1. We've got x of minus 1, which is this line here, which has a value of minus 4. So this should be equal to minus x of n. When we bring the minus sign out in front of the signal here, that means that we are timesing the amplitude by -1. So we've got a value of 4 here. 4 times -1 is also -4. And we can say that this signal is odd. As you can see, all the other signals in both directions are the same. We can also check the conditions for evenness. These are x of -n is equal to x of n. For this signal to be even, all of these impulses on this side would have to be made positive, and then we would have an even signal. There are 2 very important signals in DSP that have these conditions. The first one is a sine wave. A sine wave, by definition, is an odd signal. You can see that it has oddness around the y-axis. An important even signal is a cosine wave. We can see that it has evenness around the y-axis. Okay, let's get back to impulse decomposition. So we're going to decompose this signal x of n into its individual weighted shifted impulses. So the signals you'll see here are 0 for most values, but each of them has an impulse component of x of n. I've highlighted them in separate colors so it's clear which ones belong to which. So you can see that x of -4 has this value of 1, and we've decomposed this into x of 0n. Then we have a value of 2 at -3, which is this one from our original signal. A value of 3 at -2, which is this one from our original signal. And I'm sure you can see what's coming next. We've got the next one. And finally, I've highlighted 0 as well. I couldn't decompose the whole thing because I ran out of space, but hopefully you get the idea of how we're splitting this signal up and how, if we summed these signals below our x of n together, how they would form this left-hand side of our original signal. For this reason, all of our decomposed signals need to have the same length n as our original signal, so that when it comes to adding them back together, we can add all the points point by point to obtain the original signal. Oh, is that where I'm going? Yep. Cool. So, last month I spoke a bit about introduction to systems, and I showed this block diagram, which is generally how a system is shown in most textbooks for DSP. You've got some input, a box which represents the system itself, and some output y of n. Last time that I showed this system, I put a capital H on it, and I said that I would explain why in a later episode. This time we've got h of n, and that is because that is the notation for the impulse response of a system. And the impulse response is simply the output of a system when an impulse is used as the input. So I want to define linear time invariant systems. Last time, at the end of the talk, I spoke about the conditions for linearity. This is a system has to be homogeneous and it has to be additive. Homogeneous meaning that if we scale the input by some factor, then the output is scaled by an identical factor. And additivity meaning that if we add 2 signals together in the input, then those 2 signals pass through the system without being interfered with. So those are the conditions for a linear system. For a time invariant system, we can add some shift to the input signal and preserve the shift in the output signal. All of these conditions are about preserving something, whether that's a scaling factor, an addition, or a shift. Why is it useful to be able to express a signal as its weighted, shifted impulses? last episode we introduced the idea of systems. One way we can input signals into systems to give this idea of, one second. Oh, sorry. I'm getting used to these controls. So this image is taken from the book, The Scientist and Engineer's Guide to Digital Signal Processing. This book was recommended to me by Fabian Rengiles, someone you might know. It's a very good book. And I chose this particular picture because it visually describes quite well how you would decompose a signal into its impulse components, feed them through a system, each time gaining the impulse response for each additive component, and then using synthesis, or plainly adding, add them together to receive an overall output signal. And the whole idea of this theory is that when you feed the individual impulses through the system and add the impulse responses, you receive the same output as you would if you fed x of n through the system without decomposition. And I've notated here what it looks like when we have a weighted shifted impulse. And these are expressed in terms of our original impulse, which we saw was 0 everywhere and had a value of 1 at the origin. So we can see here that we have a minus sign out in front. That's because our signal has a value of -1. And it has a shift of 4, because it's shifted 4 places from the origin, where the original impulse would usually be. We have this one, which has a scaling factor of -2, because this impulse has the value of -2, and a shift of +3. We have a scaling factor of -3 here for this impulse, and a shifting factor of 2. It might seem a bit counterintuitive that we add to shift to the left, but this is what you can think of as an advancement if we're moving this way, and a delay if we're moving this way. Another common signal you'll come across is the unit step signal. This is a function that resembles a step with a value of 0 everywhere until point 0, n equals 0, where it suddenly steps up to 1 and has the value 1 for all n after that. This is what we call a causal signal, meaning that it has non-zero values after the origin and 0 values for all n before the origin. For that reason, if you wanted to make any signal causal, you could multiply it with the unit step function in order to receive a causal version of your other signal. Let's talk about real exponential signals. An exponential function is an exponentially increasing or decreasing time series. Real exponential signals refer to an exponential signal where both the base and the exponent are real numbers. We want to look at real exponential signals because we'll later get into looking at complex exponential signals, which are a fundamental building block of DSP. And I wanted to show you what the real exponential signals look like for different values of alpha. So if we ignore the scaling factor capital A in front just for a moment and look at what the effect of alpha is on each real exponential, we can see that when the mod of alpha is larger than 1 and alpha is positive, we get an increasing exponential. This is for a value of 1.2. We can also see that when the mod of alpha is larger than 1 and for a negative value, such as minus 1.2, we have this oscillating, increasing exponential. when the value of alpha is smaller than 1 and alpha is positive, we have this decaying exponential. And when the value of alpha is smaller than 1 and is negative, we have this oscillating exponential, but in the other direction. Next, we're going to look at some basic signal operations. First, we're going to look at time shifting. This is nothing but adding a shift in the positive or negative direction to a signal. We can shift a signal to the left or to the right. When we shift the signal to the left, it is a negative shift, but it is called advancement of the signal. And when we shift the signal, oh, they're the same. Plus is going to be to the left, and that's an advancement. Minus is going to be to the right, and that's a delay. I'm just going to have a drink before we shift the signal. So this is an example of advancing a signal. We can see here that I've added a shift of +2, which means we're going to have a shift to the left. If you're experienced with this, you can do it just by visually seeing, like, okay, this used to be 1, now -1, now it's going to be -3. But one thing we can do is plug in the values for n. So for this signal, we want the output x of n plus 2. Say we want to find the output at point 0. We're just going to plug in 0 in the place of n. 0 plus 2 gives us x of 2. So we're going to take the signal at x of 2 and place it down here at 0. Then we want to find for n equals -1 in our output signal. Plug it in here. -1 plus 2, +1. So we go and grab x at +1, bring it down here. Same again. Want to find y at -2, plug in. I'm sorry, I just realized that. Oh no, you have a screen there. I thought I was standing in the way of everyone there. All good, all good. Okay, y -2, plug that in, -2 plus 2, x of 0. And you can see that that comes down here. So we've shifted the signal to the left 2 spaces. Nice and easy. Oh, forgot about my highlighted ones. Now I've got my laser pen. Okay. This is another example. This time it's just to the right instead. So we have our output signal, y of n, x of n -2, and y of 0. Let's calculate that. Just plug in 0 -2, get x of -2. So we're going to take that, bring it down here to 0. You can see what's going to happen next. All of the other values are going to follow, and we shift it 2 places, causing a 2-sample delay. The next operation is time reversal. We can see that this is an example, another example of an odd signal. In time reversal, the notation is x of -n. So we want y of n, the output, to be x of -n. And what this -n does is it means that we are going to flip the signal around the y-axis. So simply all we do here is just whatever value we have at x of n, for the output we make it negative, and vice versa. So you can see here that this is a version of this just flipped around the y-axis. There we go. Final operation is time scaling. Time scaling is denoted by a scaling factor a that goes inside the brackets next to n. So we're multiplying n by some scaling factor. What we need to know here is that when a is larger than 1, we have a compression, and when A is smaller than 1, we have an expansion. This is another one of those things in signal processing which is a bit counterintuitive, like with the shift, when you think it would be positive going forward and negative going back. But yeah, it's just one of those things. And we'll see what I mean next. So this one is going to be a compression. We also call this downsampling. And that is a condition when the A is larger than 1. So here the example is y of n should be x to n. So whichever n we have, we're timesing by 2. So if we come down here, we want to find y of 0. 2 times 0 is 0. So with time scaling, if we have a value at the origin, that will always stay the same, because anything times 0 is going to be 0. The next one, y of 1, we want to find, we plug in 2 times 1, as it's 2 times n, and then we get x of 2. So x of 2 comes down here. The thing I will say about time scaling is that, unlike time scaling in continuous time, we actually lose information here. As you can see, we've got 5 samples in our input signal, and down here in the output, we're actually just left with 3 samples. That's because, say we try and calculate y of 2, plug in x 2 times 2, then we're given x of 4. Now, n equals 4 in our original signal is 0, so we actually have nothing there that we can bring down here to put at y equals 2. And the same for minus 2, so we're left just with this compressed version of our original signal. So the opposite is expansion, and also referred to as upsampling. This time we have an A which has a value less than 1. You can express it like this, but you can also express it like 0.5 times n. You'll see both in DSP textbooks. Let's have a go at upsampling this signal. So we want to find y of 0, plug in 0 divided by 2, 0. Like I said, 0 is generally preserved when we're talking about time scaling or when we're talking about reversal. What about y of 1? So if we plug in y of 1, we've got a calculation for n where 1 over 2. So that's going to give us 0.5. So with discrete signals, we don't actually have 0.5 as a value of n. We can only represent integer samples. So this is something we can't do. So this one will just be left as 0. Y of 2, 2 divided by 2, x of 1. So our value that we had for x of 1 is being expanded over here. And you can see how this is causing an overall expansion of the signal. Our signal started off at minus 2 to 2 for non-zero values, and ended up with values for minus 4 to 4 for non-zero parts. We can see also that for 3, we do 3 over 2. What's going to happen? We don't have an integer value, so we cannot do that. So y of 3 is also 0. And then for 4, we can see that we shift this one that used to be 2 way out here to 4. So we can say that for any odd n, we can't have a value when we're doing upsampling. What we can do is we can use interpolation to fill in these missing signals or missing gaps. Yeah, I think that describes upsampling. And yeah, that's my final slide. Thanks for rattling through that with me.
All right, thank you, Rachel. I think you said you prefer not to answer questions during the talk, right? But you'll be around, right?
Because it's it's just because it's every month, so.
Okay.
But people can always ask me questions on the Discord or Twitter. My handle is Madam Modular.
All right.
Or on LinkedIn.
Amazing. Thank you so much.
Thank you. Shall I take this?